So what we're going to go through today is actually how we can go from coming up with a traditional design like we see on the right-hand side to something like we see on the left-hand side for battery cold plate. But first, let's just do a little bit of an introduction to Synera for folks that aren't familiar with us. So Synera is a low-code platform, a visual programming environment that really connects engineering tools from a lot of different places together. And so, what is low code? Well, really it's about creating workflows pretty seamlessly, pretty easily, just by dragging and dropping a few items here. So here I've made a sphere. I'm going to say, actually, I want that sphere to have a radius of, let's say, 10. And we can see that automatically updates on my screen there with this level of interactivity. Now, obviously, workflows get much more complex, as we saw, than just generating spheres. But the idea here is that we can start to string together different components to actually create a cohesive workflow here. Now, these workflows typically involve things, as I said, much more advanced in spheres. It might be we're going to use a MATLAB script in our process. Maybe we want to use Python. Or, as I said, most often connection to parametric CAD tools. We see people building integrations to, let's say, Creo, where we want to actually take a Creo file and start to parametrically modify that and use that inside our workflow, inside our process. All of these are possible inside Synera today because our goal is really providing connections to every engineering tool that you may be wanting to use in your workflow and your process. So let's dive into the workflow that we've come up with today to come up with this amazing cooling plate design with Diabatix. So obviously we don't start with the end result here. We're going to go back through and take a look at our workflow. And this all started with a simple configurator we started to build out. Now, here, if I turn on the display, we can actually see we've got what looks like a battery module here with a variety of cells packed inside of it. Now, as a user here, we can see I've got my own little function here to really play around with some different properties and parameters here. And we'll dive into actually what it goes into to make this. So I'm actually going to change the type of cells that I'm using, and we're going to see the whole process start to update. Recalculating our KPIs like number of cells, capacity, power, weights, and also most important, our cooling plate that we're actually going to optimize with Diabatix. So here we can see we can play with a number of these different values. Maybe I want to go back and change this to a much smaller design because my ideas for a module have changed. Now, the key thing here is because we've created a function and really encapsulated our knowledge here about this coming out with the first order representation of the battery pack here, we're able to really rapidly iterate. And so, of course, with rapid iterations, you come up with some high-level designs, but then we really have to go and optimize. But let's take a look at what this function actually looks like underneath the hood. So we've actually gone in our user-defined function here and specified a variety of different battery cells that we want to use in our design process here. Now, we're able to define with those battery cells, the name of them, the current, diameter, weight, price per unit, all of these types of things that are going to go into our calculation to help us determine which type of battery we want to use. Now, the other thing is we've gone in and defined some basic geometric constraints that we want to have with our design here. Some length of our pack, the width of the pack, height, some basic configurations that you'd expect for a rectangular module. The other nice thing, though, is if we wanted to, we could select different shapes and use that in our configurator as well, because we've created this own custom function here. Or we could even type in parametric CAD geometry to this as well. Let's go back to the box. Now, throughout the process, we're going to capture some of these key values. And as we start to, in this case, define our own sorting and nesting algorithm, we can see all of the different components of that laid out here in the workflow, very easy to understand, until at the very end, we start to get into some of the other variables that we want to play with here. So we have the spacing between our cells. I want to use this 2D nesting algorithm because we're going to stack batteries on top of each other, not really a Tetris type operation in 3 dimensions, but rather 2 dimensions. And then at the end of this process, we end up with a variety of outputs that we're calculating here, whether it's the number of cells, the total price, the voltage, and all of this is going to go back into our core workflow. And obviously this is, if we look at it from afar, a pretty, medium-sized complexity workflow. But if I want to consume this now, it's super easy in the end because I've just included this, all of that's hidden away behind the scenes, and have a few easy values to play with here. Even, if I want to change the thickness of my cooling plate, all of that's encapsulated inside my workflow. Oh, maybe I've gone a bit too high there. I can't nest all of my cells with the cooling plate I've selected. But we're going to see this again update and start to generate a variety of KPIs here. So the next step of the process is really, okay, we have this, I would say, kind of first level design. Now we need to take that and really start to optimize this, right? And the nice thing is, normally you'd go ahead and maybe define through traditional means a cold plate like this, right? A lot of manual CAD interaction goes into creating this, and we can automate some of that with Synera, but we really want to step this up and get it to a fully optimized design. And so we're going to do that with our integration with ColdStream, where we've set up the entire process for running the workflow right here inside Synera. So it starts with applying our login credentials, pretty standard stuff, but then we get into the nitty-gritty of simulation, where we start to apply different materials, material properties, and things like that to the different regions of the model. Again, all of this is set up so it's associative. So as we were to change our configuration coming out of the battery configurator, we'd be able to start kicking off more simulations, more optimizations to really come up with a variety of different designs to help us hone in on what's going to be the exact right fit here. So again, we can zoom out a little bit and just see the process that we've developed quite easily here inside Synera. So defining for the different regions, the different material properties. Of course, what simulation is complete without some boundary conditions, where we're going to apply some inlets and outlet flow. And again, all of this really easy to do inside the visual environment here. All of your workflows stored for you. So as you go back and maybe make a few tweaks and changes, it's right there for you to work with. Now, obviously, the optimization process takes a bit more than the 5 minutes that we've been here, but we can take a look at some of the results that we've extracted from the previous designs. And so we can see here a greater delta T between our inlets and outlets through this designed workflow that's been optimized with ColdStream versus the traditionally manufactured one or traditionally designed one that you would do in your CAD tool. And again, the nice thing here is because we've encapsulated this into our workflow, as we start to make changes to those configurations, we can really go back and easily iterate on these design possibilities. And to dive into really the capabilities of ColdStream, I'm going to pass it over to Roxanne to show some of what goes into this optimization process on our side.